Hello learners, in today's class we'll learn about Carnot's engine. This is the topic for B.Sc first year second sem. So Carnot engine. Carnot engine is a thermodynamic cycle that gives maximum efficiency of a heat engine. Okay, it's an ideal concept that works for the thermodynamic principle for a heat engine. Okay, it gives a maximum efficiency of a heat engine while working between two temperatures. It works between two temperatures, T1 and T2, that is hot and cold temperatures. And it uses reversible thermal, adiabatic expansion, compression, okay, and isothermal also. So Carnot's theorem. An engine that works between two temperatures T1 and T2 of hot and cold reservoirs cannot have efficiency more than that of the Carnot engine. So here the theorem is saying that any engine cannot have the efficiency as that of the Carnot's engine's efficiency. So that is Carnot's engine efficiency is much greater than any engine. Okay. So the efficiency of Carnot engine is independent of nature of working substance. Okay, it is Carnot engine is independent of working substance. What is the nature of the working substance? It's independent of that. Okay. Next. Carnot's engine efficiency formula. So this is the Carnot's engine efficiency formula. Eta is equal to 1 minus T2 by T1. Okay, where eta is the thermal efficiency of the engine. T1 and T2 are the temperatures between which the engine is working. T1 and T2, hot and cold. So efficiency depends only on temperature range. But we can see with the formula. We can see from the formula that efficiency is depending only on the temperature range. Right? Now we'll see the derivation. Okay, we'll see the derivation. Once again. Derivation of Carnot engine. Okay. Now let us consider the graph. Okay, let us consider the graph. A Carnot cycle for a heat engine with an ideal gas as a working substance. So we are considering an indicator graph, that is P at the y-axis and V at the x-axis. Okay. Now we have four processes here. The ideal gas is going through four processes. Okay, so this is the first process, here is the second process, third process and fourth process. Okay, fourth process. So here at A, from 1 to 2 it is going isothermal expansion. Okay, from step 1 to 2 it is going on isothermal expansion process. Isothermal expansion process is going on. Here at 1, or let us take it as A, the pressure is P1, volume is V1 and temperature is T1. Which process? Isothermal process. Isothermal expansion process. Okay. Now here at B, or at the second step, pressure is P2, volume is V2, temperature is T1 only. Okay, T1 only, because it is isothermal expansion, and in isothermal we know the temperature will not change, temperature is constant, so T1 only. Okay, from 2 to 3 what process is going on? From 2 to 3 adiabatic expansion is going on. Okay, adiabatic expansion is going on. At step 3 or at C, the pressure will be P3, volume let it be V3 and temperature let it be T2. Okay, T2. So from 3 to 4, step 3 to 4 isothermal process is going on, but compression. Okay, isothermal compression is going on. Okay, and here at the fourth, or we can take D. Okay, D. Which process is going on? Here isothermal compression. No? So here at D point, pressure let it be P4, V4 volume and T2 is the temperature. And from 4 to 1 again adiabatic compression. Step 4 to 1 carries adiabatic compression process. Adiabatic compression. Did you understand? Step 1 and 2 isothermal expansion. Step 2 to 3 adiabatic expansion. Step 3 to 4 isothermal compression, and again coming to initial position adiabatic compression. Okay, here the variables were P1, V1, T1. Here also P2, V2, T1 only. And here at the third step P3, V3, T2. And at the fourth step P4, V4, P4, V4, T2. Okay, these are the steps that are going on. Okay, now suppose we have hot reservoir at temperature T1. Okay, temperature T1 we are having hot reservoir. Like let me draw here. This is a T1, and cold reservoir at temperature T2. This is a cold reservoir. Okay, let this be cold reservoir. So the heat is absorbed by temperature T1, and here there is a working substance. Okay, here there is a working substance. Some work is going on here by the by extracting the heat from the T1. Okay, how much heat is extracted? Let us suppose it as Q1, and after the work is done, some amount of heat is rejected, or some amount of heat is flown away to T2. Okay, let that be given as Q2. Right? So, and afterwards, after this, this T2 again gives the reversible engine some of its heat, and the reversible engine works starts here, and after the reversible work is done here, the amount of heat, some amount of heat again released to T1, reservoir T1, and this process goes on like this. Okay. So this is the working substance, and this is reversible engine. Okay. Now at step 1 and 2, as I have said you, at step 1 to 2, which process was going on? Isothermal expansion was going on. Okay. In isothermal expansion was going on. So the work done formula for isothermal, that is at work done at step 1 to 2 will be equal to Q1, because Q1 heat is being flown, mu R T1 log V2 by V1. Okay, let this be equation 1. And at step 2 to 3, as we have discussed, adiabatic expansion was going on. Okay, adiabatic expansion. So work done for adiabatic expansion at 2 to 3 will be mu R T1 minus T2 by gamma minus 1. Okay, let this be equation number 2. Similarly, at step 3 to 4, from 3 to 4, which process? Isothermal but compression. So what will be the work done? 3 to 4, work done from 3 to 4 will be, there is Q2 mu R, same like this, same like first equation, but little change. Mu R, here temperature is T2. Okay, logarithm V3 by V4. Let this be equation number 3. Okay. Similarly, at step 4 to 1, that is coming back to its initial position. So here what was the process? What is the process that is going on? That is adiabatic compression is going on. So the work done formula for step 4 to 1 is equal to, what will be? Mu R T1 minus T2 by gamma minus 1. This is the equation number 4. Now let's add all the work done expressions to get the total work. Okay. Now can you see 1, 2, 3, 4, right? So to get the total work W, we have to add 1 to 2 plus work done 2 to 3 plus work done 3 to 4 plus work done 4 to 1. So we'll write the expressions we got. Okay, what were the expressions we got? See, mu r t1 log v2 by v1 was the first. Next, mu r t1 minus t2 gamma minus 1 by gamma minus 1 plus mu r t2 log v3, okay, v3 by v4 and plus mu r t1 minus t2 by gamma minus 1. Okay, on adding all these equation, see here, third and fourth are compression process, right? Third and fourth are compression process, so we have to write minus here. Okay, minus. So on simplification, we get these two terms is cancelled. These two terms will get cancelled. So W is equal to mu r t1 log v2 by v1 minus mu r t2 log v3 by v4. Okay, this is a work done formula for the Carnot's engine. Now let us see the efficiency. Okay, efficiency of the Carnot engine. And the formula, as we have discussed earlier, that is eta is equal to W by Q1, or 1 minus T2 by T1, or 1 minus Q2 by Q1. That is 1 minus Q2 by Q1 also. We can write. So we know Q2 and Q1. Okay, this is Q2 and this will be Q1. So what we get? 1 minus, okay, let's do W by Q1. Okay, we know W. Okay, this is the W. Mu r T1 log V2 by V1 minus mu r T2 log V3 by V4. Okay, divided by Q1 means mu r T1 log V2 by V1. Okay, so what can we do here? So when we take common mu r, okay, when we take mu r common at the numerator, we get like this. Okay, V3 by V4 divided by mu r T1. Here mu r gets cancelled. So the next step we can write T1 log V2 by V1 separately with the denominator. This term also separately. So this again gets cancelled. So what we get here is 1 minus T2 by T1 log V3 by V4 divided by log V2 by V1. Okay. So keeping this aside, now see, as step 2 to 3 is an adiabatic process. It's an adiabatic process. So what we can do is, we can write T1 V2 gamma minus 1 is equal to T2 V3 gamma minus 1. So from this we can write V2 divided by V3 is equal to nothing but T2 by T1 power 1 by gamma minus 1. Okay, due to being adiabatic process, we can write like this. Okay. Next, similarly, step 4 to 1 is an adiabatic process. Again, okay, it is an adiabatic process. So here also we can write V2 by V3 is equal to T2 by T1 1 by gamma minus 1. Okay, so the before equation we got, the before equation was V2 by V3. This is the equation that we got now. So after this also, this is for 1 second. This was step 2 to 3, and for step 4 to 1 also we get as T2 V4 gamma minus 1 is equal to T1 V1 gamma minus 1. We can write V1 by V4 is equal to T2 by T1 power 1 by gamma minus 1. Let this be equation B. Okay, let this be equation A. So from A and B we can write V2 by V3 is equal to V1 by V4. Or we can also write like V2 by V1 is equal to V3 by V4. Okay, now what was our equation? See, this was our equation, right? So if we write V3 by V4 here, and here also if we write V3 by V4, at two places if we write V3 by V4 and V3 by V4, what happens? We can cancel out this. Okay, this time we can cancel out, because here we can write V3 by V4 as explained here. So what remains? We remain with only 1 minus T2 by T1. Okay, W is equal to 1 minus T2 by T1, right? So sorry, this is eta. Okay, eta is equal to 1 minus T2 by T1. What is this? This is the efficiency of Carnot's engine. Okay, Carnot's engine efficiency we have found out. Okay, in the two processes, isothermal expansion, adiabatic expansion. In the next two processes, isothermal compression and adiabatic compression. Okay, that was about the Carnot's theorem, and we have found out the efficiency also. So here, as I have shown you the diagram, so here. So we have a hot reservoir here, we have a cold reservoir here. Hot reservoir working at temperature T1 and cold reservoir is working at temperature T2. Okay, Q1 heat is absorbed from the hot reservoir and released to the cold reservoir in the form of heat after being some work done. Okay, so we need to take engines, the engine system from temperature T1 to temperature T2 and back again to temperature T1. So each step of the cycle can be reversed. So heat taken from Q2 from the cold reservoir at temperature T2 does some work again on the system and transfers that Q1 to the hot reservoir that is working under the temperature T1. So theoretically this can be reversible, like a refrigeration system. So to prove the Carnot's theorem, we have to imagine a reversible Carnot engine. Okay, reversible engine that is working between the sink. Okay, this can be said as sink and this can be said as reservoir, hot reservoir. Okay, now so the Carnot heat engine is an ideal type of heat engine. It is not there practically. It's an ideal type only that converts heat energy into some work. Heat is converted to work. So it's a most efficient way one can understand because of the law of physics. So it was first explained by Carnot in 1824. Okay, that is why it is named like this.